This is Euclid Book 10, proposition number 34. And here is the illustration. Looks familiar, doesn't it? Okay. To find two straight lines incommensurable in square, which make the sum of the squares on them medial, but the rectangle contained by them rational. Let there be set out two medial straight lines, AB and BC. Okay. This line is medial, and so is this. This is medial, and so is that. Okay. Now then. These two lines that I just showed you are commensurable in square only. Now, if you were to take those two lines and make a rectangle out of them, okay, you're going to take this line and this line, you're going to make a rectangle out of them. If you do so, the area inside of that is rational. And the square on AB is greater than the square on BC. What do you mean by that? You're going to take this line right here, and you're going to make a square out of it. Okay? And the area inside that square is going to be larger than the area in another square. Now, what other square are we talking about? If you take BC and you make a square out of it, the area inside of that will not be as much as the area inside of the square AB. And you can draw this out for yourself. Okay? And if you decide to do so, and you leave me a link to your video, I will put it down here in the description below. Okay. Now, the square on AB is greater than the square on BC, which we just told you, by the square on a straight line incommensurable with AB. So whatever line it's talking about here, that line is going to be incommensurable with AB. But if you make a square out of that line, then that area, if you add that to the area of the square of BC, it will become the square of AB. That's what I was trying to say. And this is by Euclid, Book 10, proposition number 31. Let the semicircle ADB be described on AB. Okay. So now we're drawing this semicircle. Okay. Let BC be bisected at E. That means that this line right here is the same length as this line right here. BE is the same length as EC. That's what it's saying. Okay. Yeah. Let there be applied to AB a parallelogram equal to the square on BE. Okay, so what we're going to do is we're going to draw a parallelogram on AB. And the area inside of it is going to be equal to the area inside of BE. So somewhere along in here we're going to draw a parallelogram. And the area inside of it is going to be equal to the area of BE. Because what we're going to do is we're going to take BE, we're going to make a square out of it, and that area will be equal to that. So, okay. And deficient by a square figure, namely the rectangle AFFB. Okay. So, hang on just a second. So now we're going to make a rectangle. Two sides of that rectangle are going to be AF, and two sides are going to be FB. Okay. And this is by Euclid Book 6, proposition number 28. Therefore, AF is incommensurable in length with FB. And that's by Euclid Book 10, proposition number 18. Okay. So, this line is incommensurable with this one. Alright. Let FD be drawn from F at right angles to AB. Okay. So now we're drawing this. And let AD, DB be joined. Okay. So now we've drawn this line and this line. Okay. since AF is incommensurable in length with FB, okay, we already said that a little bit ago, therefore the rectangle ABAF, now what's the rectangle ABAF? Okay, what we're going to do is we're going to make a rectangle, two sides of the rectangle are going to be the length of AB, and two sides of the rectangle are going to be the length of AF. So, two sides AB, two sides AF. That's your next rectangle. Okay? That rectangle we just drew is also incommensurable with the rectangle ABBF. Okay, so now we're going to draw another rectangle, two sides of which are going to be this length, and two sides are going to be this length right here. Two sides this length, two sides this length. Okay. And this is by Euclid Book 10, proposition number 11. Alright, now, after you've drawn out those two rectangles, the ones that were ABAF and then ABBF, those two areas are going to be incommensurable. Alright. But the rectangle ABAF, which you now should have drawn, is equal to the square on AD. Now, what's the square on AD? That means you're going to take line AD, you're going to make a square out of it. And all four sides of that square are going to be the length of AD. That's what it means. Okay. And the rectangle ABBF, which we drew a while back, okay, that's that rectangle we said was AB and BF. Okay, two sides AB, two sides BF. Remember that rectangle? Okay. The area inside of that is equal in size to the square on DB. So what are we going to do? We're going to take this line DB and we're going to make a square out of it. And all four sides of that square are going to be the length of DB. So the rectangle ABBF, that area is going to be equal to the area in the square of DB. Okay. Therefore, the square on AD is also incommensurable with the square on DB. Okay. So we made a square out of this line, we made a square out of this line. The areas in those two squares are incommensurable. And since the square on AB is medial, therefore the sum of the squares on AD and DB are also medial. Okay, so first of all, we made a square out of AB. Okay, all four sides of that square are the length of AB. Then we made a square out of AD. All four sides of this one is going to be AD. Then we made another square out of this one, which is DB. We made a square out of that. So if we add this square, if we add this square and this square together, we get the area of this square. How do we know this? Because of Euclid Book 3, proposition number 31, and Euclid Book 1, proposition number 47. And since BC is double DF, okay, now we're saying that the length of BC is double the length of DF. Therefore, the rectangle ABBC, alright, so now we're going to make a rectangle AB, two sides AB, two sides BC. And I'm sure you've already made that one by now. But the area inside of that particular rectangle is double the area in the rectangle ABFD. Okay, so now what we're going to do is we're going to take AB, and that's going to be two sides of a rectangle, and the other two sides are going to be FD. So the area of the first rectangle is going to be double the size of the area of the one we just drew. Okay. But the rectangle ABBC is rational. Therefore, the rectangle ABFD is also rational. That's by Euclid Book 10, proposition number 6. So the rectangle that was double the size of the other one, because it was rational, then the other rectangle is the double size of, is also rational. That's what they're saying. But the rectangle ABFD is equal to the rectangle ADDB. Okay, so we made a rectangle ABFD. Okay? we made that rectangle. And then we made a rectangle of AD and DB. Okay, so we made a rectangle, two sides like this and two sides like this. Okay? And those two rectangles are equal in area. And that's by the lemma. So that the rectangle ADDB, the one that has two sides AD and the two sides DB, that rectangle is rational. Therefore, two straight lines AD and DB, this is AD and this is DB, incommensurable in square. That means that if you made a square out of each one of these, the areas would not be commensurable. Have been found, which make the sum of the squares of them medial, but the rectangle contained by them rational. And that is the whole proof. I will tell you more in a future video. Stay tuned.